Hi there. Welcome to Dark Matter Day. Today we're going to have a number of presenters that will try to cover the topic of dark matter and hope that you get a feeling for both what it is and how we attempt to detect it.
So the honest answer is we really don't know. There is a broad scientific agreement on its existence, but we still do not know what it actually is. So it could be something much lighter than an electron, billions of times lighter than an electron, and it can be something tens of times heavier than the sun. It is true that it cannot be anything in the middle of those things, but that is the range of possibilities that different studies are facing. So that is the honest answer. We need to find out.
Well, it's very different than what we thought 30 years ago, thanks to these very sensitive measurements. And it shows us a universe which is made up of really three major components. The matter that is represented in the stars and us, material like us, is only about 4% of the total. This dark matter makes up about 26%, and there's a quantity called dark energy, which was observed recently. It's something that Einstein's theory allows, and they study supernova, and they find that the most distant supernova are so far away and so fast that it appears as though they have been accelerated more than the standard attractive force of gravity would allow. This is referred to as dark energy and is the subject of many other experiments. So today we discuss dark matter and ways to observe it.
Most galaxies lack the mass which they would need in order to exert the gravitational force which they do. So we have this conundrum where we have a good understanding of gravity, but with all the visible mass in a galaxy, we cannot explain their gravitational force. So what we think is happening is that these galaxies have a different kind of matter. This matter is what we are calling as dark matter. Dark because it does not interact with electromagnetic radiation. So it is a special type of matter, unlike our ordinary matter, which you and I are made of, which the planets and stars are made of. So this dark matter does not interact with electromagnetic radiation. It neither absorbs or emits light.
Another indication of the properties of dark matter is shown by a couple of colliding galaxies. And what you see here is a picture taken and superimposed on the sky. The pink matter is what has happened to ordinary matter, and it's measured with X-rays. But if you use that gravitational lensing, you can infer that the actual main mass, which is represented by the blue spots added artificially, is much farther out. It obviously has passed through without being impeded by collisions, showing that dark matter is very weakly interacting. If you put all this evidence together, you can conclude that dark matter can be represented as weakly interacting massive particles. So we have quite a robust theory of how the universe has evolved since the Big Bang about 14 billion years ago. And this has come from many measurements and combined with the theory of cosmology. And here's the overall story associated with that. about 14 billion years ago, there appears to have been a cataclysmic event, which is usually referred to as the Big Bang, followed by a very quick inflation of the universe, in which the universe expands from about the size of an atom to the size of a grapefruit in a very short period of time, 10 to the minus 40 some seconds. After that, the energy that is translated into mass for different particles creates a soup of, a very hot soup, as you can see, 10 to the 27 degrees Celsius, of electrons, quarks, and neutrinos and other particles. That cools off as the universe expands, and it eventually becomes cool enough that protons and neutrons, the quarks can combine to form protons and neutrons, and after about 3 minutes, protons and neutrons can come together to form the nucleus of hydrogen or helium atoms. And then after about 300,000 years, the electrons can form neutral atoms. And at that point, actually, one has the situation where light can shine through. That light is cooled off so that it's presently about 2.7 degrees or so above absolute zero, and it's called the cosmic background radiation. And it's measured explicitly by satellite-based instruments. Turns out that this cosmic background radiation, when studied in detail, is quite remarkable in terms of what it can tell us about the formation of the universe and its evolution. This is a map taken with the Planck satellite of, on the left, of the variation, only about a spatial variation of about 10 to the minus 5 or so. But it can be used to fit to models of how our universe evolved. Ordinary matter and dark matter interact quite differently as the universe evolves because, of course, there's very little interaction we see for dark matter. And that then leads to the quite remarkable data from Planck. You can actually see a scattering of data points here taken from the Planck satellite, and the data points are the averages, and the line is a theory of different components of the universe referred to as the lambda cold dark matter model, and it's remarkable how well it fits the data.
Well, we really don't know the such characteristics of dark matter, and that's why a wide range of data detection experiments has arose in the last decades, and other ones more and more sensitive are foreseen in the next years. As the colleagues have already pointed out, these dark matter particles interact pretty rarely with ordinary matter, but still they have some kind of interaction with that besides the gravitational one. Specifically, assuming they are thermal relics from the first expansion of the universe, we would expect them to weakly interact with the ordinary matter, same way as neutrinos do. Still, differently from neutrinos, they must have a mass of at least a few GeV, as otherwise, no way the galaxies could exist. So we know that they weakly interact, and we know that they are pretty massive. So this is why we call them weakly interacting massive particles, WIMPs, where massive can extend up to about 100 TeV. Now, this candidate is pretty promising, not only because it would answer to other questions coming from theoretical physics, for example related to supersymmetry, but also because we can actually design a wide range of experiments to test this hypothesis. And that's where DEAP comes from. DEAP 3600 is an experiment designed for the direct detection of WIMPs. There are also other dark matter candidates going up to a few dozens of solar masses, the so-called primordial black holes, as well as down to 10 to minus 22 electron volt, the so-called fuzzy dark matter, where fuzzy just reminds that at such low masses quantum mechanics dominates. As also Andrew will underline, our experiment is actually sensitive also to other dark matter candidates different from WIMPs, but still our main goal, our first aim, is the direct detection of WIMPs or otherwise the exclusion of their existence.
There is no one answer to that question. Different experiments try to leverage different physical phenomena to detect dark matter. We should keep in mind that although extremely rare, dark matter is still expected to interact with ordinary matter. So if we have enough of ordinary matter under investigation for a long enough period of time, we should see some of these rare events. In DEAP 3600, we employ liquid argon as the target material. When dark matter particles collide with argon nucleus, although extremely rare, we expect to see a few of these events, and these events will lead to several interactions which would lead to UV radiation, 128 nanometers to be precise.
DEAP 3600 is conceptually very simple. It's an ultra-pure spherical vessel made of acrylic that contains 3.3 tons of liquid argon. Now, this volume is scrutinized with 255 photomultiplier tubes, and each of those generates an electric charge every time they receive a photon. And looking at the amount of light that is produced, the time pattern of the light that is produced, the distribution, so which PMT has seen more photons and which one has seen less photons, then we can reconstruct a lot of information of the event and find out if it is potentially dark matter or it is not.
Now, all of these regards the inner vessel. The acrylic vessel is coupled to the photomultiplier tubes via acrylic light guides. The photomultiplier tubes are set on a stainless steel sphere, which is the one that you can see now, 2.5 meters of radius, which is connected to the long neck, which allows for the cooling of the system and eventual refilling of the chamber. The system is set in a cylinder of about 7 meters of diameter and 7 meters of height, filled with ultra-pure water, observed by another set of photomultiplier tubes. This is the so-called muon veto and allows for the suppression and eventual rejection of particles which are not WIMPs, so background, coming from outside the chamber, so from the rocks surrounding the detector, which is set at the SNOLAB, 2 kilometers underground in Sudbury, Ontario.
So why liquid argon hides two questions: why liquid and why argon? Why liquid? Because it's 800 times more dense than gas. So we want our target to contain as many argon nuclei as possible, so that our chances that a WIMP hits one of those is larger. And then why argon? So reasons are mainly three. So first, you need the light to be produced, and then you need the light to reach your detector. So another important property is that argon is transparent to its own scintillation light. So we have a big detector, and even if the light is produced in the center, this light will reach the PMTs that are on the surface of the acrylic vessel. An extra important feature is that the light is produced in a way that allows you to distinguish different kinds of interactions. So mainly if the interaction happens with the shell of electrons that the atom has, or with the nucleus of the argon. And then we know that the WIMPs, or we expect that the WIMPs interact with the nucleus, and the interactions that you see that correspond to interactions with the shell of electrons, you know that it's not a WIMP, and you know that you can reject that. So it allows you to discriminate or focus on the events that are potentially interesting to you.
So in DEAP, we're searching for interactions of dark matter particles with the argon nuclei in our detector. Basically, the theory tells us that there is a large cloud of dark matter surrounding the galaxy, and as the Earth is moving around the sun and the sun is moving around the galaxy, we have a constant wind of these dark matter particles blowing through us at all times, called the dark wind. Yeah, I know, very spooky, right? So the idea is that dark matter is so ghostly that it just passes through the Earth without noticing anything. So that means the number of dark matter particles is more or less the same everywhere we look. So this cup I'm holding has some dark matter in it, and also it's so comfy. Our theory tells us that the average total mass of all the dark matter particles in this cup has some value, but it doesn't tell us the number of particles in this cup. That means that we could have a very large number of particles if they're all very light, or we could have a smaller number if they're heavier. So in DEAP, our main goal is to search for dark matter particles that weigh about as much as a few atoms put together. At these masses, at any given time, we expect somewhere in the ballpark of a few thousand dark matter particles per cubic meter. So the DEAP detector is about a sphere with a radius around 85 centimeters. So that's a volume of about 8 cubic meters. And this means that at any given instant of time, we have around 20,000 dark matter particles sitting in it, traveling through it, depending on how heavy they are. That's a lot of particles. However, as I said before, our theory tells us that these dark matter particles are so tiny that these interactions are extremely rare. Instead, they just kind of fly right through the detector, dodging all the argon atoms in it. So we're trying to measure the interaction rate of dark matter particles with the argon atoms in our detector. Given what we currently know, even with tens of thousands of particles in the detector, we expect that we'd have to wait for at least several years before we see any interactions that we can uniquely identify. In this time, if we see something, then great, we can report a measurement. If we don't see anything, then instead we know that the interaction strength of dark matter has to be even weaker. And so we might have to wait even much, much longer to see anything, and make much bigger detectors. So in other words, the dark matter could be even more ghostly than we previously thought, like a super ghost. So rather than reporting a measurement of the interaction rate, we just place an upper limit on how strong these interactions are. But ultimately, we're looking for something in the ballpark of interaction rates around a couple of events every few years, and maybe even much smaller than that. So while searching for dark matter, we use these very carefully made detectors that achieve extremely impressively low levels of background in them. And the extraordinarily low noise levels in these detectors is really what enables us to perform dark matter search. So once the detector is operational and collecting data, a lot of the work then boils down to understanding our backgrounds, calibrating our detector to a very high level of precision, and using this calibration to build detailed models of our backgrounds and signals. So we can design clever analysis tools for differentiating between our backgrounds and the dark matter signals that we're looking for. We then have to accurately predict how many of these backgrounds we might mistakenly label as a dark matter interaction, and how many dark matter particles we might misidentify as a background. Once we've designed an analysis that can do all of these things, we can build hypotheses. So for example, we can say if there are no dark matter interactions in the detector, how many events do we expect to see purely from backgrounds that we've misidentified? Then we can ask how many events we expect to see if we have a dark matter particle that has some interaction strength. Once we figure out all these models, we apply our analysis to the data, and we count the number of dark matter-like events that we see. This number is statistically significantly different from the prediction under the background-only hypothesis. We can say that we made a detection. and we can find the range of interaction strengths that would be consistent with what we observed. Otherwise, we didn't make a discovery, and we instead asked what the strongest interaction strength could be before it predicts that we'd see some number of dark matter events that we can say for sure is not consistent with what we observed. In this way, we're able to place an upper limit on how likely dark matter is to interact with argon nuclei, and this provides fundamental input to figuring out which dark matter model might be the correct one and telling us where to look next. No. No, so far all of the observations that we've made have been consistent with our background-only hypotheses, and so we can say where dark matter isn't, but we don't yet know what it is.
If we tweak the way we think dark matter interacts in our detector by looking at different possible mechanisms of interaction, from the theoretical side, it turns out that you get some enhancements in the way or in the rate that dark matter should interact in DEAP 3600, and that in particular allows DEAP to be sensitive to subtleties like different distributions of the velocity, say, of dark matter in the Milky Way, which in turn can provide enhancements and lead to DEAP actually having the highest sensitivity for certain interaction processes in contrast with our xenon counterparts elsewhere in the world. The next interesting thing that we've been looking at are so-called MIMPs, or multiply interacting massive particles. So unlike WIMPs, which we expect to only interact once in our detector, a MIMP will interact many times as it traverses the argon in the detector. And the signatures from MIMP interactions, in contrast with WIMPs, should be much more distinct, i.e. you'll have very high energy signals or lots of scintillation light produced, whereas in a WIMP interaction you have a single nuclear recoil that produces very low energy signatures. So and the last two are actually items that may sound a bit familiar, particularly in that they're produced in the sun. So the first is we're actively searching for solar axions. So axions are hypothetical particles that, if our understanding of physics beyond the standard model isn't totally out to lunch, they could in principle solve what's called the strong CP problem. And last but not least, everyone at SNOLAB's favorite is solar neutrinos. So SNOLAB is named for the SNO experiment, which searched for solar neutrinos to try to explain the solar neutrino problem. We're not necessarily doing that scale of work here. However, what we're trying to do is make the first observation of solar neutrinos in a dark matter detector. So if that works out as nicely as I hope it does, we should be able to make statements about what we think the flux is of neutrinos from the sun, and then also what the interaction cross sections of electron neutrinos are in argon, which is an interesting area of nuclear physics research as well, because we don't know a lot about the structure of these interactions beyond a few measurements.
Yeah, what comes next? That's a great question. Since I joined the lab, I've been spending most of my time on DEAP 3600, and I'm still spending a bunch of my time doing analysis for that project. The question, though, is what are we going to do next? So far, we haven't seen dark matter, and all signs indicate we're going to need more sensitive detectors to do that. And there's a couple of really exciting things going on looking for that. The first is 4 collaborations that have built detectors throughout the world, Mini Clean and DEAP 3600 at SNOLAB, the ARDM detector at the Canfranc lab, and the DarkSide program at LNGS have all got together to form a large global liquid argon dark matter collaboration. What that allows us to do is basically take the best of all our work and put it together for the next generation. What we want to do is build a larger detector so we have more exposure. So DEAP 3600, 3600 kilos of liquid argon, is going to be expanded to DarkSide 20K, which will be 20,000 kilograms of liquid argon in the active measurement region. A much larger detector that we'd like to run for 10 years. Beyond that, we're looking at a project, probably at SNOLAB, for a 300-ton scale liquid argon detector. We don't know exactly what that will look like. We are doing the conceptual design now. Remember, the DEAP program started in the early 2000s, and it's 2021, and we're still working on it. These projects take a generation to build and operate and get the data from. So even though we're building the DarkSide 20K detector, we're taking all the lessons we've learned from that and putting that towards the design of a future detector. This continuous work is really quite fun. We learn from our mistakes, we learn from our challenges, and we've learned also from our successes and what we need to do to build the next best thing. The other fun thing about thinking about the future is who you get to work with. It's true, we just sometimes, the scientists sit around on a Zoom call and discuss possible detector designs and how it would work and what things we need to do. We also need to work with engineers. We need to work with technical people. The skilled tradespeople who build these experiments have a big input into how we build them. If we don't take their advice, we're going to come up with something that actually isn't constructible. So we need all sorts of effort, all sorts of knowledge, all sorts of different types of expertise to make this sort of thing happen. And I have to say, this blank piece of paper fun stage, how do we design the next great thing beyond DarkSide 20K onto this 300-ton scale Argo project, is an awful lot of fun.